Assalamu alaikum and welcome back. In this session, I want to talk about one of the most fundamental distribution that is used in network performance evaluation studies. It is often used for modeling various time metrics. This is the exponential distribution. The exponential distribution is a continuous distribution in which the random variable can take a continuous range of values. And we're interested in finding out the probability distribution function for this random variable. We'll also be seeing that exponential random variable has many generalizations, and we'd be covering many of them because they are used much in queuing theory, in which we make a lot of use of exponential distributions. So let us start by talking first about the exponential distribution. Exponential distribution rises naturally whenever we have Poisson arrivals. So if you recall, we have earlier talked about Poisson arrivals in which we are given the average arrival rate in an interval, and then we can calculate the probability of various arrival counts. So if you have such a distribution, if your arrival follows a Poisson distribution in which you know the average rate, and the arrivals are due to many independent processes. So if you have many independent factors, if you recall, we said that Poisson distribution is the limiting form of binomial distribution in which you have a very large number of trials and a very small probability of that trial being successful. So if that is the case and you have Poisson arrivals, the time it takes between two successive arrival is the inter-arrival time. And we use the exponential distribution to model the inter-arrival time when we know that the arrivals are coming according to the Poisson distribution. Poisson distribution is very important for network performance evaluation studies because classically, almost all of the basic queuing theory actually depends on Poisson arrivals and exponential inter-arrival times. So let's now see the exponential distribution in some more detail. Exponential distribution can be thought of as the continuous counterpart of the geometric distribution. If you recall, we said that a geometric distribution counts the number of trials it takes to get the first success. In continuous terms, our trial now is of infinitesimally small duration. And as we mentioned in Poisson distribution, you are considering a lot of trials, and the probability of each of the trial resulting in a success is very small. And if we take the product of the number of trials, n, with the probability p, this actually gives us the average rate. So this lambda is actually the parameter that we use for defining the Poisson distribution. When we talk in terms of the exponential distribution, so we have a direct analogy with the geometric distribution. There we are measuring the number of trials it takes to get the first success. Now, instead of trials, we're going to talk in terms of time. So now we are measuring the average amount of time we expect before we get the next success. And in terms of exponential distribution, typically the next success means the next arrival. Another important point which both the geometric distribution and the exponential distribution share is that both of them are memoryless. So if you recall again, when we talked of geometric distribution, we said that the probability or the expectation of the next success does not depend on the history. So even if you had very atypical history, let's say you are tossing a number of coins to get the first heads, even if you had a lot number of heads previously, or you've had a long streak of tails, it does not matter when you want to calculate the probability of having the next heads. Similarly, when we talk of the continuous exponential distribution, it does not matter what happened in the past. The average duration that we expect to wait for the next arrival remains a constant. Because of this, the exponential distribution is called a memoryless distribution. This property is also known as the Markov property, and it is extensively used in queuing theory. The reason being that with this Markov property, exponential distribution becomes very easy to analyze. So because of its mathematical simplicity, often it is said that it is seen that we are using exponential distribution for modeling the inter-arrival time. In fact, it has been now shown repeatedly that actual inter-arrival times on any network, be it a LAN or a WAN, they typically follow a heavy-tailed distribution, which is very different from a Poisson distribution and an exponential distribution. Both of them belong to the class of mild randomness distributions. We'll be seeing later in today's session that what are the different kinds of heavy-tailed distributions and what implication does it have. An example of an exponentially distributed time would be the time that you expect to wait for your next phone call. Assuming that your phone arrivals are Poisson distributed, that is that they have an average rate of arrival. So we are ignoring the fact that people sleep during night time, the average rate during night would reduce, and so on. For simplicity's sake, we are assuming that all during the day and all through the night, the average rate of telephone arrivals is a constant. If that is the case, the time that you expect to wait for your next phone call would be exponentially distributed. And receiving some calls or even receiving a call just now does not prevent a call from coming after some time. In fact, the expected duration that you expect to wait before the next call would remain the same. And that is a hallmark of the exponential distribution. Let's now consider an example of exponential distribution. And the question is that measurements have shown that the average length of a phone call is 3 minutes. Assuming that the length of the call is exponential random variable, what is the probability of the call lasting for more than 6 minutes? So to understand and answer this, we need to see the formula that we have for the exponential distribution. So we go back and talk of the formula now. The formula is a very simple one in which you have a single parameter, and that single parameter is the average waiting time till the next event comes. And this is actually the reciprocal of the lambda parameter that we've defined for Poisson distribution. So we've seen that Poisson distribution and exponential distribution are intimately tied together. Whenever you have a Poisson arrival process, you would have exponential distributed inter-arrival times. So it is because of this reason that the parameters are shared as well. For Poisson distribution, you have the parameter of lambda. For exponential distribution, the parameter is 1 over lambda. So we have just a single parameter, which is often called the scale parameter, because changing this scales the distribution. It either makes the distribution more spread or more condensed. It does not change the shape of the distribution. For an exponential distribution, the mean of the distribution is 1 over lambda. Or in other words, it is the parameter that we've just defined, beta. Also, the standard deviation for an exponential distribution is identical to its mean. So mean is equal to standard deviation is equal to 1 over lambda or beta. So we saw for Poisson processes and Poisson distribution, the mean is identical to the variance. In this case, the mean is identical to the standard deviation. So you can see the formula here. On the left-hand side, we are given the probability density function, and this function is only defined for positive values of x. So the formula is 1 over beta multiplied by exponential, in which the exponent is minus x over beta. And we also can calculate the cumulative density function for the exponential distribution, that is calculated as 1 minus e raised to minus x over beta for non-negative values of x. So Now we are in a position to answer the question that we set for ourselves. The measurements of phone call have shown that the average length is 3 minutes. We want to know the probability of a call exceeding 6 minutes. So beta in this case would be 3 because that is the mean duration between calls, and lambda because of that is 1/3. But for this example, we only have to make use of beta. So we can use the cumulative distribution function, and if you recall, the cumulative distribution function, the CDF of a particular value is the probability of taking that value or less than that value, equal or less than that particular value. So if we're interested in finding out the probability of a call lasting more than 6 minutes, then we would have to make the calculation of 1 minus the cumulative distribution value for the value of 6, because 6 is what we are interested in finding out the call exceeding this time. So if we do that, we see that we are interested in 1 minus f of 6, where f function is the cumulative distribution function. And when we are doing 1 minus cumulative distribution function, we are actually determining the complementary cumulative distribution function, which actually tells us for a value what is the probability of exceeding that. And that is what we're interested in this question. So if we make the calculations, this comes out to be 13.5%. And this actually underscores the point that exponential distribution, while it is used a lot in queuing theory and in network performance evaluation studies, it is still a mild distribution. And when we see and when we talk of self-similarity of network traffic in future sessions, we'd be seeing that actual network traffic has a lot more variation. And because of that, exponential distribution is only useful as a first approximation. And almost always it is very simple for actual accurate depiction of network traffic. So after having discussed the exponential distribution, we can talk of some generalizations of exponential distribution, in which we talk of families of distribution, of which exponential distribution is just a special case of. With suitable parameters, that general family of distribution can, appear like other distributions. So the first family of distribution of which the exponential distribution is a special case is the gamma distribution. Gamma distribution has 2 parameters. The first parameter is the shape parameter. This is called alpha, and in some textbook you might see this being referred by other letters, but as long as we are consistent, it does not matter. So we will be calling this alpha. The scale parameter is beta, and for both of these parameters we have values of more than 0. The probability density function of the gamma distribution is shown on the screen now. You would see that this distribution only exists for positive values of x. And you see that on the screen you have in the numerator 2 terms. One of the term is the exponential term, and the other one is a polynomial term. And with the interplay of these terms, you would see that for different values of alpha and beta, we can change how they interact. So because of that, we can get different shapes. Another interesting property of this distribution is the gamma function, which you find in the denominator. So gamma function is actually a generalization of a factorial. You would know what a factorial is. So in a binomial distribution, we saw factorials. So that is represented by some number followed by an exclamation mark. So if we want to generalize the factorial for non-integer values, because up till now you would have only seen integer values of factorials. So if we want to use it for non-integer values, we use the gamma function, and we define the gamma function of n plus 1 as n factorial. And we can use this function for calculating values even for non-integer values. So the mean and the variance of this distribution can be seen on the screen now. I want to talk about something very important about this distribution. This distribution is a general distribution which can look like some other distributions with appropriate choice of parameters. In fact, gamma distribution, as mentioned before, is a generalization of the exponential distribution. इसका मतलब ये है कि हम gamma distribution के parameter अगर set करें तो हम उसको exactly exponential distribution बना सकते हैं. So if we make a choice of alpha, which is the shape parameter, as being equal to 1, then this thing becomes exactly equal to the exponential distribution. And exponential distribution and gamma both have also a shape parameter referred to as beta. हम gamma distribution को ऐसा भी समझ सकते हैं as the sum of some independent random variables. In fact, this is useful when you want to model the time, let's say, a packet spends in some network. A network can be represented as a network of queues. बहुत सारी queues एक circuit उनका बना हुआ है. So as you enter and before you exit, you're going to spend some time on various queues. So for each queue, you can represent the queue by its service time. And if we are thinking of representing the service time by an exponential distribution, the overall service time would be a sum of multiple exponential random variables. In such a case, gamma distribution can be used for modeling that. Gamma distribution is even more general. In fact, it can represent, or it can become, the chi-square distribution as well. If you recall, when we talked of goodness of fit test, we mentioned the chi-square distribution, which we said was a kind of a sum of multiple unit standard normal variates. So we can even model that distribution by a gamma distribution by appropriate choice of parameters. If you have the chi-square distribution with k degrees of freedom, then you would require for gamma alpha to be set to k by 2, and the beta parameter would be 2. So you see that gamma distribution is very versatile. It can imitate many other distributions by appropriate choice of parameter values. So an interesting case is when the shape parameter is some integer value. हमने एक केस तो उसका देख लिया, when the integer value is 1. When the integer value of alpha is equal to 1, then gamma is exactly an exponential distribution. But you can also have other integer values like 2, 3, 4, or in general m. So if you have alpha is equal to some integer m, then this distribution is called as an M-Erlang distribution. And this is a very useful distribution used in teletraffic theory. The idea is that you have multiple stops in which each stop is going to take service time of some exponential random variable, and the rates are constant for each one of these stops. If you have m stops, then the time it takes to traverse all these stops is represented by the M-Erlang distribution. You can see the M-Erlang distribution on your screen now, and you would see that there is a direct link between gamma distribution and the Erlang distribution. If we set the beta parameter to 1, and for various m, you see that the gamma distribution and the Erlang distribution are exactly the same. Okay, now let us see the gamma distribution for various scale factors. So the scale factor is going to tell us how spread out the distribution is and how quickly the tail is decaying. So when the shape parameter is equal to 1, which is the graph shown on the left hand side, then this is exactly the exponential distribution. And you can imagine the beta parameter here to function exactly like the beta parameter functioned for the exponential variable. When alpha is different, and in fact alpha can take even non-integer values. हमने special case देखा when alpha is equal to integer values, and we said that that is the Erlang distribution. But it can also take non-integer values. For example, chi-square distribution में अगर odd number of degrees of freedom है, फिर you would have a non-integer value of alpha. So now we are representing on the right hand side various lines in which you have the gamma distribution shown for shape parameter alpha is equal to 2. When alpha is equal to 2, you would see that the general idea remains the same, that beta tells us about the distribution spread or how quickly will the tails decay. Let's now talk about the gamma distribution for different shape factors alpha. We've seen that when alpha is equal to 1, this is exactly the same as an exponential distribution, and you have a monotonically decreasing function. If you have alpha less than 1, you also have a monotonically decreasing function. As the alpha value increases above 1, you would have a mode, or because you have an interaction between the polynomial part and the exponential part, you would have a mode or a hump. And as we keep on increasing the values of alpha, the shape would become more and more symmetric. Okay, let's now talk about another kind of a distribution, which is the phase type distribution. So a phase type distribution can be thought of as a combination of multiple exponentials. So this can be in the form of a sum, because you may think of forming a line of links in which you have multiple stops. The service time on each stop is represented by an exponential random variable, and now the rate of these random variables may actually change. So if you see the graph on the left hand side, you see multiple stages and you have rates specified for each one of them. Stage 1 has the rate of mu1, and all till stage m, where the rate is mu m. You would see that this is different from the gamma distribution and the Erlang distribution, in which you had constant rates. The important point here is, in a hypo-exponential distribution, which is a kind of a phase type distribution can use a combination of hypo-exponential distribution stages and hyper-exponential stages, which we will cover shortly. In a hypo-exponential distribution, the variance is less than what you would expect in the exponential distribution, and that explains the hypo part. You would see that the coefficient of variation, which is the standard deviation divided by the mean value, for a hypo-exponential distribution is less than 1. If you would recall that for an exponential distribution, this is exactly equal to 1, because the standard deviation is exactly equal to the mean value. So we are interested in this when we want to model some behavior of packets going across a network. So if we have some empirical distribution in which we observe that the variance is less than what we would expect in an exponential distribution, we can make use of hypo-exponential distribution. On the other hand, you can talk of a hyper-exponential distribution, which is referred to as a mixture of exponential random variables. In that case, you have multiple stages, again having different service rates, and then you can choose them in a mutually exclusive manner by some probability. That, for example, we would choose the first stage with this probability, the second with this probability, and so on. So we can refer to this circuit arrangement as a mixture of exponential random variables. And when we do that, the coefficient of variation is actually more than 1. So with the combination of hypo-exponential distribution and hyper-exponential distribution, the phase type distribution can practically construct any distribution that is positive valued. And this is very useful because in many cases, simple exponential distribution is not a good fit to the data that we have. But using a phase type distribution, we can have multiple phases, and these phases may be summed. When we are summing them, this is the hypo-exponential distribution, and we may be even having a mixture of these phases. In that case, you have a hyper-exponential distribution. You can actually make some combination of these two distributions as well to get the distribution shape that you want. Okay, this is very useful, but we perhaps will not have time to talk about this in any more detail, but this is very useful for fitting distributions to data. Another general class of distribution that is very useful and which is also a generalization of the exponential distribution is the Weibull distribution. So a Weibull distribution is very useful for modeling time and also for reliability modeling. The Weibull distribution, much like the gamma distribution, also has two parameters, alpha and beta, where alpha is the shape parameter and beta is the scale parameter. So this distribution also, like the exponential and like the gamma distribution, only exists for non-negative values of x. So we can see the formula of the density function on the screen now. You would see that this is similar to what we had for the gamma distribution, but you would see that the gamma function is now missing, and also the exponential part is a little different because now you have an additional exponent of alpha. And this is important because now as we change alpha, the shape parameter actually changes more conspicuously. The cumulative distribution function is also shown on the screen now, and we note that the exponential distribution is a special case of the Weibull distribution when both of alpha and beta are equal to 1. So let's now see the Weibull distribution for various values of alpha. So you can see graph on your screen now in which you have the Weibull PDF for the fixed scale parameter beta is equal to 1, and we are changing the alpha parameter. So you would see it's a clear pattern that as you start increasing the shape parameter, the shape changes quite a lot. When you have alpha is equal to 1, this is the same as the exponential distribution. And when you start increasing the alpha value, initially the distribution is right skewed. Right skewed ka matlab, if you recall, is when the tail is leaning towards the right hand side. As you keep on increasing the value of alpha, it starts becoming more symmetric. Alpha is equal to 3.6, you have a symmetric distribution curve. For higher values of alpha, you would see that you have a left skewed curve. So for appropriate values of alpha, you can actually fit your model to most practical data sets. And this is the reason Weibull distribution is so popular. And when you have alpha values less than 1, your Weibull distribution becomes a long tail distribution. This is something very useful as well because many practical data sets have a long tail distribution. They are not like the exponential distribution in which the tails decays exponentially. In other words, for a distribution like the exponential distribution, it is going to be exceedingly rare to find a value which is very far from the expected value. But for a long-tailed distribution, you would have some outliers as well. And many practical data sets have outliers that are very far away from the mean. So to model those sets, Weibull is very useful, and we can model long-tailed sets with alpha values less than 1. If we change the scale parameter now, which is beta, keeping alpha constant, we keep alpha constant as equal to 1, we see that shape parameter is similar in function to what we would expect. We expect that the beta parameter would help us visualize how quickly the distribution is decaying. So this works in a similar manner to what our intuition would say. Okay, now finally I would like to compare gamma versus Weibull, and because while they may have qualitatively similar density functions, they have very different values. So for identical parameter values, we have drawn Weibull versus gamma, and you see that as you change the shape parameter, which is alpha, you see that it has a more conspicuous effect on the Weibull distribution. So depending on your topic of interest and the data set that you have, you may explore both of these distributions. Let us now shift topics. Up till now, we've only discussed the distributions belonging to Mediocristan, in which the variance was limited and you would not expect some, very extreme value. But the real world is more wild than what we would expect if we were to believe Mediocristan. So much of practical data that we cover, especially in network performance evaluation studies, may be thought of as belonging to Extremistan. In Extremistan, the distribution is such that it is possible, and in fact the probability is non-negligible, that you would have very extreme values. The world of Mediocristan works when you are modeling processes that are constrained by physical and biological limitations. So as an example, we've talked of the heights of people. Because of biological reasons, you will never have a person, in the recorded history, we don't have a person who was 100 times the average height. You never would have heard about someone being 500 feet tall because of physical limitations. But in many of the processes that exist in Extremistan, there is no such constraint. For the example of wealth, there is no constraint. In a capitalistic society, in fact, having more wealth creates more wealth. And because of that cycle, you would see that some people have all the wealth, almost all the wealth, and most of the people live below the poverty line. And that is Extremistan for you. We have a direct analogy of this in network performance evaluation studies, in which you have many resources. For example, if you consider a network, you would have only a few users that are using a bulk of the available bandwidth. You consider the number of people living in a city, they also follow such a distribution in which most of the people belong to large cities. And when a city becomes a large city, it is going to attract more people, and then it is going to widen the inequality. Similarly, in languages, you use some words much more than other words. You do not have a random distribution over all the possible words. You also do not have even what we would call a mild distribution. Some words are actually used a lot more than other words. So these distributions belong to Extremistan. The reason is that if we were to believe in the mild randomness world, we are going to underestimate many extreme occurrences. And you would see a common theme in our discussion that some of these outliers are actually going to have a big impact on your evaluation. A single outlier can change the average value by a lot. This is not the case in Mediocristan, where the average value and the extreme values are not very far from each other. So you can see on the slide here, archetype of a heavy tail distribution in which the tail does not decay as swiftly as you would expect in an exponential distribution. Because of that, in the central graph, you see that some values are way beyond what we would expect given just the average value. So, in fact, when we discuss fractals, one of the pioneers in this area who has actually influenced the people who have coined the word Extremistan as well, Benoit Mandelbrot, actually talks of this as focusing on the grass and missing the very large trees. If we only focus on the low values, we are going to miss some very high values which are going to have a very significant effect on your performance. On the right-hand graph, you see that those very extreme values are going to actually change your usual statistics that you use to quantify performance measure. So if you're thinking of the average, this extreme outlier is going to make the average not robust. In that case, the average is going to keep on moving. In certain cases, normally we expect that if we have a large enough sample, we are going to converge to the mean value. But in some cases, when you keep on increasing the sample size, you would keep on increasing the average value. In that case, we have a problem because our usual statistics would not work. So let's now talk about the size rank discrepancy that we would expect in Extremistan. As an example, think of your college library. It would have a lot many books, but typically not all of those books would be checked out. In fact, there would be many books that will not be checked out at all since the library was created. And there would be some other books which were checked out so many times, a lot more than what you would expect from the average value. This is what is known as informally and empirically as the 80-20 rule, which says that 80% of the results are going to come from 20% of the effects. And this has been empirically observed in many different settings. This is a signature of a distribution which is known as the power law distribution, which belongs to the world of Extremistan. We're going to talk of heavy tails and long tails, and we're going to make a subtle distinction between them, but they generally mean that it is quite possible to sample a very large value which is very extreme and very much distant from the typical value. So we can talk of a discrete distribution which is characterized by the Zipf's law, and the Zipf's law is actually, it was initially worked out by someone who was working in the field of linguistics, and he was measuring the frequency of usage of certain words, and he discovered that the usage is actually quite anomalous in the sense that some words are used much more than the other words. In fact, the distribution that you would find using a Zipf's law is what you can see on your slide. And for this to work, we have to rank the data. So on the x-axis, जो आपके पास values हैं वो असल में ranked हैं according to some order. The leftmost bin of the histogram represents the first, in this case we can imagine the first word, the most popular word. तो एक तरह से हमने popularity के हिसाब से x-axis पे rank किया हुआ है in a decreasing order. अगर आप count को अब measure करें तो now there is a distinctive form to the distribution that you have. And this is the case when the frequency of occurrence is actually a function of some power of that attribute. This is represented as the formula that count is inversely proportional to alpha power of rank. And alpha is typically equal to 1. In that case, count would be inversely proportional to the rank, and you also have some constant here. So to understand this in some more depth, let us have a look at the relation between the power law distribution and the exponential distribution. So for that, we are going to graph together two functions. One of them going to follow the power law function, and the other one is going to follow an exponential function. So the power law function is going to represent a power law decay, in which things are decreasing, but according to the power law distribution method. And for the exponential function, we are also modeling decrease, but now the decrease is exponential. So for the power law decay, the formula that we are going to use is equal to y is equal to x raised to minus 2. And this is typical of power laws, in which the value that you are interested in, be it the frequency or the count, is actually a function of some power of that attribute. In this case, y is equal to x raised to minus 2. The attribute is in the base. अगर आप observe करें, x base में है और exponent minus 2 इस case में है. It can be other values as well. It is usually referred to by the variable alpha. But the important thing is that in a power law, the base is the variable and you have some fixed exponent. On the other hand, if we talk of the exponential decay, now the base is fixed and the variable is in the exponent. While this may seem trivial, it has huge bearings on how the decay happens. So let's see now how this thing works out. So we're going to plot power law versus an exponential function on linear scale. So you can clearly observe that as the value of x increases on the x-axis, you always have exponential decaying at a faster rate than power law. That is in our example. But you may have other examples in which for a certain time it may be that power law is decaying at a faster rate. But in the long run, it is always the case that exponential decay is much, much more swift. So to expand on this more, we draw another graph on which we are representing the same information but now on a log-log scale. So you can see that on your slide now, and we observe a clear pattern now. We see that the power law is represented by a linear function, a straight line, and that is the signature of a power law. Whenever you are interested in seeing if some function is a power law, you usually graph it on a log-log scale and see if it is following a straight line. The meaning which this implies is that you have a constant exponent, and because of that your decay is going to happen much, much more slowly, and you would have larger values for very high values of x. On the other hand, when we talk of the exponential decay function, it is going to happen very, very quickly. This is because you have x in the exponent. उसकी वजह से जब x increase करता है तो आपका decrease बहुत तेजी से हो जाएगा. So we can clearly see now then that exponential distribution gives very less opportunity to the extreme values to occur because the decay is exponential. अगर आप observe करेंगे on the log-log scale, as the value of x increases, the slope also increases. इसका मतलब ये है कि rate of decrease है, it is going very, very fast, exponentially fast. But when we talk of the power law, the rate of decrease is linear, or when we represent it on a log-log scale, which is much less extreme. जब आपकी rate of decrease much less extreme है, इसका मतलब है कि extreme values के occur होने के chances काफ़ी comparatively ज़्यादा significant है. I hope the point is clear. Okay, let's now talk about power law distributions, which we also refer as heavy tail distributions. तो अभी हमने distinction तो कर ली. We've seen how power law distributions are different from exponential distributions. Power law distributions ज़्यादा extreme तब होते हैं when you have alpha value in the range of 0 and 2. In such a range, we refer to the power law function as a heavy-tailed function or a heavy-tailed distribution. When you have higher values of alpha, तो आपका जो decay ज़्यादा जल्दी हो जाता है. इसलिए extreme values की occur होने की probability एक तरह से काफ़ी कम हो जाती है. It is only in the case when you have alpha between 0 and 2 that your decay is very, very slow, and because of that your tails are going to be heavy. So to show this, we make use of what is known as the log-log complementary distribution plot. So a complementary distribution plot is basically 1 minus the CDF. In other words, if you're interested in finding the value of CCDF of some value, you're going to see what is the probability of getting a value more than this. So let us now discuss one of the most important heavy tail distribution, almost the archetype of a power law distribution. This is the Pareto distribution. So a Pareto distribution has two parameters, alpha, which is the shape parameter, and a location parameter, which various authors refer to by different symbols, and many people also omit it. So if we have this location parameter as equal to 1, you may also omit it, but we are going to use this in our formula. The density function for the Pareto distribution is shown on the screen now. You would see that the value of x has to be more than the location value that you've set, जो हमने xm define किया है. Also, the Pareto distribution is defined for the shape parameter values of alpha between 0 and 2, because it is in this range that you have heavy tail behavior. Outside this range, heavy tail behavior is not shown. You can also see the cumulative distribution function, the f of x, and you can also see the CCDF, which is 1 minus the cumulative distribution function, and you see the same power law function hold here. You see that, for example, in the CCDF, that the CCDF value is equal to xm over x raised to the alpha exponent. And this is exactly what we were covering before when we talked of the power law. If in case where you have xm is equal to 1, then this is exactly equal to x raised to minus alpha. And we've seen earlier that if this thing is plotted on a log-log plot, you would find a line representing the relationship. And this is shown here, where you can see that the slope of this line is actually dependent on the alpha value that you choose. So this is going to be between 0 and 2. And as you increase alpha value, you would see that this starts coming to the left-hand side. In other words, for higher values of alpha, the decay is going to be more sudden. You're going to decay quicker. If you have lower values of alpha, you would see that the decay is now less steep. So you're going to include a lot more of your tails. So another important point of the Pareto distribution is that the variance is only defined for the Pareto distribution if alpha is more than 2. And we've talked of how we use Pareto distribution in the range of alpha is equal to 0 and 2. In this range, you don't have any variance. And this may seem quite strange to you, but this is how heavy tail distributions work. In fact, if you decrease the value of alpha below or even keep it equal to 1, you would see that the mean is not defined. So this is a little different from the classical statistics that we have been studying up till now. In that, when you have some random variables and you take a sample from some distribution and you take the average of it, you're going to converge to the average true value. But in such a distribution where no variance exists, where no mean exists, you would see that there is no mean to converge to. And because of that, for a small sample, you would have some mean value. But as you keep on increasing the size of your sample, you would see that your mean would keep on changing. And if you have a sample of infinite size, you would see that your mean also becomes infinite. Let's see this through an example. This example is for the Pareto distribution alpha is equal to 1. And for alpha is equal to 1, you have infinite mean and infinite variance. So if you observe on the x-axis, we have the sample serial numbers, the values that you're drawing out from this distribution. And the sample values are on the y-axis. The typical value where most of the mass is concentrated in this graph would be less than 10. You would see that most of the values are actually less than 10. But then you have some very, very extreme values. As an example, I've highlighted this extreme value of 1207.3, which is more than 100 times the typical value. Compare this to the height example. Would you expect to see someone having 100 times the average height? Obviously not. But in Pareto distribution, the chances are quite significant that you would have an extreme sample value. Let's build on this example to show how much is the probability of getting an extreme value in Pareto distribution as compared to exponential distribution, and we do this in more quantitative terms. So you can see an example on the screen now, and we are to compare the probability of getting a value of 100 times the mean in exponential distribution versus Pareto distribution for different values of alpha. So for an exponential distribution, because we are interested in getting a value of 100 times or more, we are going to use the CCDF function. And when we make that calculation, this comes out to be e raised to minus 100, which is 1 into 10 raised to 43, which is an exceedingly small number. For all practical concerns, this thing will never happen if we were to believe this model. In a Pareto distribution, on the other hand, if we assume an alpha value of 2, so if we make the calculations, the mean comes out to be equal to 2. And the probability of getting a value more than 100 times this is 1 in 40,000, which is still very small, but a lot more significant than the value we had for exponential distribution. And when we have alpha is equal to 1.1, this comes out to be 1 in 2216, which is very much possible. And this highlights difference between Pareto distribution and the exponential distribution. In practical terms, it has been seen that inter-arrival times are usually more better fit by Pareto distribution for different values of alpha than the exponential distribution which we have been assuming. This has big concerns because if we see this example, the exponential distribution seriously underestimates the occurrence of large values. So this is very important to note. So let's now talk about a class of distributions whose tails decay at a lesser rate than the exponential distribution, but not as slow as the power law distribution. We refer to this class as the class of sub-exponential distribution because this comes in between the very fast rate of decay of the exponential distributions and the very slow rate of decay of the power law distributions. We're going to cover just one example of this, and that is the log normal distribution. The sub-exponential distributions are also called as long-tail distributions because they have some aspects of heavy tails, but they are not really heavy tails as power law. So we give them a special name, which is long-tailed distributions. So a log normal distribution is a distribution if we take the log of which it becomes a normal distribution. So on the screen now you can see the density function of this, and I note here that the mu and the sigma value that you have in the formula is not actually the mu and sigma value of the original distribution, but it is the mu and sigma of the transformed distribution. On the bottom of the screen you can see two graphs. On the left hand side you can see the original distribution, and you can see it is right skewed. So the meaning of right skewed being that the tail extends much to the right hand side. If you transform this data onto a logarithmic scale, you would see that this distribution then becomes roughly symmetric. So this is in fact the hallmark of a log normal distribution. The logarithmic transformation of the original data makes it a normal distribution. A practical example of an application of log normal distribution is in fitting to the data that was empirically observed by Vern Paxson in his work when he observed that FTP data has a lot of variation. So if we were to graph the file sizes of FTP transfers on the linear scale, we would see a graph which we can see on the left hand side of your screen now. And practically we can just see one building on the left hand side and much of the other data is hidden. But still you have a lot of variation in data, and we can see that if we take a logarithmic transformation on this data, and we can see the data after transformation on the right hand side, and we now see that this is roughly symmetric now. So we can say that this data actually is coming approximately from a log normal distribution. So with this we've come to the end of this discussion on heavy tail distributions that belong to the world of wild randomness. We'd be covering in future sessions how long-tailed and heavy-tailed distributions have a lot of implications on network performance evaluation. We also covered that while we are using light-tailed distributions as approximations of network traffic, this is often not a very good approximation. I'll see you next time when we talk more about these things. Assalamu alaikum.